Okay, so let's have a look at energy in collisions. Well, we've already, right at the beginning of this course, we've looked at collisions, and we know we came up with the principle of the conservation of momentum, that the total momentum before a collision is equal to the total momentum after a collision. So we know that momentum is conserved. That's just, we're good with that, we know that. Well, there's also a similar principle for energy, the principle of the conservation of energy, which hopefully you know, and that says that energy cannot be created or destroyed, but only transformed from one form to another. Well, we're talking here about total energy because it can change from one form to another, but nevertheless, it is conserved. So this is really important. So collisions, including explosions and as well, momentum is conserved and total energy is conserved. But there is something else, and that is the fact that kinetic energy is not necessarily conserved. And when kinetic energy is conserved, we call that an elastic collision. And when kinetic energy is not conserved, we call that an inelastic collision. So kinetic energy doesn't have to be conserved, and whereas total energy does. And so when kinetic energy is not conserved, we say the collision is inelastic. But when kinetic energy is conserved, we say the collision is elastic. So the question then becomes, like, how do you know if a collision is elastic or inelastic? How do you test for that? Well, you might have an idea, but let's go through an example. Let's go back to our trains. Remember our railway carriages in the very first momentum conservation example that we did. And we had, before the collision, we had the two carriages kind of moving towards each other, one 3,000 kilograms at 4 meters per second, one 2 meters per second but only 2,000 kilograms. And then after, they kind of linked together and we calculated their final velocity, which was plus 1.6 meters per second. Well, to see if it's elastic, we need to find out if the kinetic energy before and after is the same. So we just do some calculations. So first of all, we find the total kinetic energy before. And before the collision, we can do that quite easily. We find the kinetic energy of the first carriage, so it's a half times mass times speed squared, a half times 3,000 times 4 squared. And we add to that the kinetic energy of the other carriage, the other body, so it's a half times 2,000 times 2 squared. Now notice, kinetic energy is half times mass times speed squared, not velocity, but we could put minus 2. It doesn't matter because the minus would disappear anyway. Minus 2 squared is also 4. But we're just interested in the magnitude of the velocity of the speed. Well, if we evaluate that, then we get 28,000 joules. So that's the initial kinetic energy in the system. So the question, is it elastic or inelastic? We need to find the kinetic energy after. So let's do that. So after the collision, well, it's easy. There's only one body now, and the kinetic energy is just going to be a half times the total mass of the new body, which is the two trains joined together, 5,000, times 1.6 squared. And now if we calculate that, we discover that it's 6,400 joules, a lot less than the initial kinetic energy. Therefore, because they're different, because there's some kinetic energy seems to have disappeared, then this must be an inelastic collision. The next question then is, what do elastic and inelastic collisions look like? Well, let's just go back to our train, because we've proved that was inelastic. Now, notice that the two railway carriages stuck together. And so, well, some of the original kinetic energy has disappeared. And so we can ask, well, where's it gone? Well, of course, when that collision occurs, there's going to be some noise, a clunk, and there's also going to be some heating effect during that sort of link up. And that's generally what to look out for. If we want to sort of ask ourselves, what are the sort of features that give away, without doing a calculation, that a collision is inelastic? Well, when objects join or stick together is pretty much definitely inelastic. Also, if you have a bouncing object like a bouncing ball, I mean, if you bounce if you drop a tennis ball on the ground, it bounces up more slowly than it hit the ground. So kinetic energy has been lost. So that's another good example of an inelastic collision. You might get a more or less inelastic collision from a bouncing ball depending on the type of the ball. And another example is explosions. Explosions are inelastic because if you think you have an object which isn't like the ice skaters on the ice rink, well, they're stationary at the beginning, and then suddenly they're moving. So kinetic energy has come from apparently nowhere. Well, of course, it isn't nowhere, and it's come from the muscles of the people pushing each other apart. So these are all really good examples and things to look out for, that without any calculation that you've got inelastic collisions going on. Another example might be, for example, a firework which explodes. Okay, so it's already moving at the beginning, perhaps, but the explosion is going to create more kinetic energy, a bit like the ice skaters. So that's come from chemical energy in the fuel in the firework. Chemical energy was what was stored in the muscles of the ice skaters when they pushed apart. So we have total energy is conserved, but it has to come from somewhere. And if we want to find out what an elastic collision might look like, well, sometimes you don't know without doing a calculation, but a perfect bounce is a good candidate for an elastic collision. If we were to drop one of those kind of super bouncy balls that you can buy in a toy shop down, well, they come close to bouncing up to the same height. If a ball did bounce up to the same height, it would be a perfectly elastic collision, because it means that the kinetic energy the speed just before it hit the ground is equal to the speed just after it hit the ground. Of course, we know that's impossible in everyday life, but some things do come close. And sometimes a question will say, assume a collision is elastic. And so perfect bounces, elastic, anything else, inelastic, and the more inelastic it is, the more kinetic energy has disappeared. If I had, as one last example, a lump of plasticine, which I kind of dropped down to the ground, well, it's going to go splodge on the ground and not bounce at all. Well, all the kinetic energy has disappeared, it's completely inelastic, and it's gone into thermal heating. So that would be another good example. So, a few questions coming up involving inelastic and elastic collisions. It's usually just part of a question. So have a go at the next ones, because they incorporate all what's come before plus these new ideas.